Hi, everyone. It's Mr. Webster here, and I'm going to walk you through the first lesson for Unit 3. The title of this lesson is The Mole, and hopefully you've either, kind of sketched out some rough notes based on the student version of this note, and so you can just kind of fill it in as we go, or you're prepared to pause the video and write notes down as we go. All right, so we're going to talk about something in chemistry called the mole. And I'm going to start by just stating that there's many examples in science and in our daily life where we use words to represent numbers. And so I think it's important to remember that. For example, if I told you that you had a pair of gloves, you would know that you had two of them. If I told you that you had a dozen eggs, you know that you have 12 of them, or a dozen donuts, you know that you have 12. And so there's a couple of other ones on the screen. A ream, you may not have heard of this, but a ream of paper means 500 sheets of paper. But these are examples where they've used a word to represent a number. And the mole is something very similar to that, as we're going to see, but just bear that in mind, that just like a dozen equals 12, a mole is also equal to a number. So that's just an important concept that we're going to need to look at. So a few points here about the mole. First of all, we know that atoms are extremely small. I can't emphasize enough that a single atom is incredibly, incredibly small. And so it's very difficult for us to make measurements when you only have a few atoms or molecules being used, okay? And a molecule is made up of, in some cases, 3 or 4 atoms. And so they're very small. If we wanted to take the mass of one atom, it would be appropriate to find the mass of maybe 1,000 atoms and then divide by 1,000. The idea that you could, take a bigger number of something and then divide by that to get the mass of one of them. But even 1,000 atoms is still pretty small. So the question becomes, is what number of atoms or molecules would be large enough so that if you were to take them and divide by that number, it becomes reasonable? Well, is a dozen, is a ream, is a million? Well, it turns out that none of those are big enough. You need a much bigger number of atoms in order to even have a tiny amount of a substance. So in the early 1800s, a scientist named Amedeo Avogadro devised a way of measuring the masses of very small particles of matter. And his big conclusion, and this was monumentous, was that he suggested that if you had 12 grams of the carbon-12 atom, so that's carbon-12 is just the one isotope of carbon, but if you had 12 grams of carbon-12, you would have this very large number of carbon atoms, but a very specific number of carbon atoms. And just like I've said before, just like words like dozen or ream or couple have a numerical meaning, he needed a word to describe how many atoms there were in 12 grams of carbon-12. And so he picked the word, the mole. And so, just so you know, if you had a dozen atoms, you would have 12 atoms. If you had a ream of atoms, you would have 500 atoms. But if you had a mole of atoms, you would have 6.02 times 10 to the 23 atoms of that substance, and that's known as Avogadro's number. And in the next few slides, I'm going to be referring to Avogadro's number as Na. That's the term, or the variable is 6.02 times 10 to the 23. And again, remember, a dozen is 12. A mole is 6.02 times 10 to the 23. So I always joke that I could send someone to Tim Hortons to get me a dozen donuts and they'd come back with 12, but I could send them to Tim Hortons to get me a mole of donuts and they would come back with 6.02 times 10 to the 23 donuts, which is a lot. Let me tell you how much of a lot it is. And again, you don't have to write this slide, but I think it's nice just to kind of put the size of that number in perspective, because it's a huge number. And what this analogy goes through is it just shows you how big numbers can become. And so this is the green pea analogy. And basically it says that if you had 100 green peas, that would fill a 20 milliliter graduated cylinder. It's a tiny, it's a small graduated cylinder that we use in chemistry. If you had 1,000,000 green peas, that would be enough to fill a refrigerator. So that's 10 to the 6th green peas. If you had 1,000,000,000 green peas, these are just these little tiny peas, you would be able to fill an average 3-bedroom house. 10 to the 12th is a 1,000,000,000,000. You could now fill 1,000 homes with these green peas. 1,000,000,000, 10 to the 15th, could fill all the buildings in a city the size of Toronto. Imagine if all of Ontario was covered a meter deep in green peas. That would be 10 to the 18th, 1 quintillion. Now, imagine that all of the continents are now covered. Everything, all land on Earth is covered 1 meter deep in green peas. You'd now have what's called sextillion, 10 to the 21. That's how many green peas you would have. And here it is. If you froze all the oceans and totally covered the whole Earth with green peas, and you had 250 planets just like Earth, all covered with green peas, you would now have a mole's worth of green peas. So again, it's just an indication to you of the size of that number, 10 to the 23. It's a huge number. Okay, well, I gave you, everyone in class, the hub, and we haven't talked about the hub yet, but the hub in this unit is going to become very important to us. And so hopefully you have a copy of the hub, and you can use this, or if not, you can print one off. I've still got one on the Edmodo page that you're welcome to print off. But here it is, and you can see the mole is so important. It's at the center of the hub, and so the mole is going to be something that we're going to be referring to a lot in the next few lessons, and certainly throughout this unit. Now, for this lesson, we're only interested in one small part of the hub, and that's the center and the bottom section. So I've pulled that one little section out to focus in on. So the mole is the center, and we're going to use a letter to represent the mole. And so we're going to use the little letter N, indicates is the mole. Okay. So we're going to use a little letter N. We're going to use a capital N to represent the number of particles of a substance. And I'm very specific about saying particles because the particles could mean atoms, it could mean molecules, it could mean formula units. And just so you guys are clear on that, the term molecule and formula unit are very similar. We use molecule when we're talking about covalent compounds, and we use formula units when we're talking about ionic compounds. And so just so you know, a good example of a molecule might be H2O. And a good example of a formula unit might be something like MgCl2. So, and obviously an atom would be just something like maybe copper. Okay, so the number of particles could be the number of atoms, the number of copper atoms. It could be the number of molecules, the number of H2O molecules, or it could be the number of formula units, the number of MgCl2 magnesium chloride particles. Okay. The other variable we're going to need today is Na, which is, of course, Avogadro's number. And it is 6.02 times 10 to the 23. Okay, so those are the three variables we will use. And so I could ask you to calculate the number of moles. And so, and maybe I should write that in there. It's not just the mole, it's of the number of moles. That you could be asked to calculate the number of moles, like the number of dozen. You could be asked to calculate the number of particles in total, which is going to be a big number. Or you wouldn't be asked to calculate Avogadro's number, but you know that. Okay, now, right at the very bottom of the hub, it shows you this triangle. And that triangle, I'm just going to move it over here just to kind of play with it a little bit. The triangle is often used to represent formulas. And some of you may have seen triangles like this for density, or you may have seen it for speed and distance. But we use it in chemistry. And what this represents is the relationship between the number of moles, the number of particles, and Avogadro's number. And the way these triangles work is that you can cover up one of the variables. If you cover up the variable that you're looking for, the rest of it will tell you what the formula is. So in other words, if I were to cover up, and here, let me use I'm going to see if I can do this. I've never tried this before, but I'm going to put a little shape on here. Like, let's say I was interested in the number of moles. And so what I would do is I would go to my triangle. Let me see if I can select this. I would cover up, here I'm just going to shade this in. You guys are watching me learn a little bit about this, working with this. So here we go. I'm going to grab it. So I'm interested in the number of moles. I'm going to cover up little n in my triangle, and that tells me that the formula is capital N over Na. So watch this. One of my formulas is the number of moles is the number of particles over Avogadro's number. Okay. Look at this. If I was interested in calculating the number of particles, I would cover up capital N, and the formula is the number of moles times Avogadro's number. So I could simply write another formula I have is capital N is equal to N times Na. And so look at this. Just by this one triangle, I have got two different formulas. I don't need technically there's a third formula, which is Avogadro's number. I could cover up Na as well, but obviously I don't need to do that because you would never need to calculate Avogadro's number because you're given it. But so those two formulas that I've written there, the number of moles is equal to N over Na, and the number of particles, which is equal to little n, or the number of moles times Avogadro's number. Those are two important formulas we're going to use in the coming slides and in your homework. We can calculate the number of moles, and we can calculate the number of particles. And the hub, you don't have to memorize these formulas or memorize that triangle, because you would get to use the hub on all tests and quizzes and exams. So I don't expect you to memorize that formula. Okay, well let's try this out. Let's try it out. I've got a couple of examples here. So here we go. We've got these are some of your homework questions. I won't do all of your homework questions, but I'm going to take you through a couple of them. This is number 13 on page 177. So it says, one way I like to stay organized, this is number 13. It says a small pin contains 0.0178 moles of iron. So that's these are atoms of iron. How many atoms of iron in total are in the pin? So they've given me the number of moles of iron, and I want to now get the actual number of atoms. Okay, well, I'm going to set up my question using a problem-solving technique, and I'm going to start by talking about what I've been given in the question. So I often write just G, but I'll write given here. And so I look up here, and sure enough, I've been given this number. And so I'm going to write 0.0178 mole. And that's the short form for moles, M-O-L-E. But anyway, it's not much of a short form. But I know that I know the variables I've been working with, and the variables are little n, capital N, and NA. Well, I need to put a variable to this. And so, of course, I look at it and say, well, that's the number of moles, so that is my little n. Okay, so I've been given little n, and it doesn't look like I'm given anything else in this question, but I'm always given Avogadro's number because that's a known value, so I'll just write it down as well, 6.02 times 10 to the 23. Okay, the second thing I'm going to write is what's required. So the R, I'll often just write the R, required. And so in this case, it says how many atoms of iron. Well, that's the number of particles, and so what they want me to solve for is the capital N. All right. The next thing I'm going to write is A, so G-R-A. It's technically the short for analysis, but really what it is it's the formula that we're going to use. And so I know, I look back at my triangle, and I see that N is equal to capital N times NA. Okay, so I'm going to come down here, and I'm going to write my formula. N is equal to little n times NA. The next thing I'm going to do is substitute and solve. Substitute and solve. So here we go. N is equal to 0.0178 times 6.02 times 10 to the 23. And I'm going to type that into my calculator and solve this. All right, well, let me give this a shot. I have an online calculator ready to go here. And so I'm going to type in. Now, I wanted to show you this because most calculators have a button called an exponent button, or an EXP. Now, typing that button is like hitting times 10. So watch what I'm going to do. I'm going to type in 6.02. And then I'm going to hit this EXP button. On my calculator, this online one, it says EXP. And look what it puts in a capital E. Some calculators will put in times 10 in there. And then I'm going to put 22. So that's, I don't have to type in times 10. I just put 6.02 EXP 22 times, and I forget what the other number is, so I'll quickly go back and look. It's 0.0178. And so I'll go times 0.0178 equals, and I get 1.071, and look what it shows me. It shows me that E, so that means times 10 to the 21. So 1.07 times 10 to the 21. So I type in here 1.07 times 10 to the 21 atoms of iron. Okay, so that's kind of how we solve these questions. Okay, let me try another one here. So I'll do number 15. Number 15 says, how many formula units? So now this is asking me for how many of the formula units are contained in this. So remember, a formula unit is that whole thing right there. So they want to know how many of those there are in 0.21 moles of magnesium nitrate. All right, well, here we go. I'm going to do my given, and I'm given that number, 0.21 mole, and I know that that's a little n, okay? I also know that I've been given Avogadro's number. I've always got that, 6.02 times 10 to the 23. And required, it says how many formula units, so it's looking for the number of particles. And I need my formula. I know that N is equal to N times Na. So I'm going to substitute and solve into that. And so I'm going to go N is equal to 0.21 times 6.02 times 10 to the 23. And that's going to give me a count of all of those magnesium nitrates. So just bear in mind that it's the entire particle. It's giving me the entire particle. And so I'll go to my calculator, and I'll clear it, and I'll go 0.21 times 6.02 EXP 23 equals 1.26 times 10 to the 23. So here we go. 1.26 times 10 to the 23, and that would be formula units. Now bear in mind that each of those formula units contains a bunch of atoms, but I'm just counting. It didn't ask me for the number of atoms. It just asked me for the formula units. Okay. You could also calculate the number of, go from the number of particles to the number of moles. So this is another example, number 21 here. I'm just going to get rid of, I'll just do 21. Okay, so 21, I could do that one. It says, okay, a sample of cyanic acid, HCN, contains that number of atoms. Okay, so let's start this off. And I'll just say here, okay, given, I'm given that number of atoms. So capital N is equal to 3.33 times 10 to the 22 atoms. Remember, the capital N is the number of particles, so that's the number of atoms. Now it says, required, how many moles of cyanic acid are in the sample? So the required is the little n, that's the number of moles. Now, interestingly, there's a little trick to this question, which is why I wanted to do it with you. It says, there's a total, it says, hint, find the number of molecules of HCN first. Because look at this, we know that every HCN, every cyanic acid molecule has a hydrogen, a carbon, and a nitrogen. So every molecule has 3 atoms in it. So technically, even though I know that there's 3.33 times 10 to the 22 atoms there, I can divide that. I can divide it by 3, and I'll get 1.11 times 10 to the 22, and that's the number of molecules present. Because I know that every molecule has 3 atoms, I just divide it by 3, and that tells me the number of molecules that are present. So actually, I'm going to use that as my capital N moving forward. Okay, I'm almost done. For my analysis here, I'm going to look back, and I'm going to go right back to my hub, and my hub tells me that little n is capital N over NA. So I've got the formula. I'm going to go put that right here. And I'm going to say, okay, so N is equal to capital N over NA. And I'm going to substitute 1.11 times 10 to the 22. That's the number of molecules divided by Avogadro's 6.02 times 10 to the 23. And let's go to our online calculator here. Let's try that out. I'll clear 1.11 times 10 to the 22 divided by 6.02 times 10 to the 23 equals 0.0184. So here we go, N is equal to 0.0184 moles. So the number of moles of cyanic acid is 0.0184. All right, I'd like you to finish the rest of those homework questions and let me know if you have any questions.